In linear algebra, an eigenvector or characteristic vector of a square matrix is a vector that does not change its direction under the associated linear transformation. In other words, if B is a vector that is not zero, then it is an eigenvector of a square matrix A if AV is a scalar multiple of V. This condition could be written as the equation, where lambda is a scalar known as the eigenvalue or characteristic value associated with the eigenvector V. Geometrically, an eigenvector corresponding to a real, non-zero eigenvalue points in a direction that is stretched by the transformation, and the eigenvalue is the factor by which it is stretched. If the eigenvalue is negative, the direction is reversed. There is a correspondence between n by n square matrices and linear transformations from an n-dimensional vector space to itself. For this reason, it is equivalent to define eigenvalues and eigenvectors using either the language of matrices or the language of linear transformations. Overview. If a two-dimensional space is visualized as a rubber sheet, a linear map with two eigenvectors and associated eigenvalues lambda1 and lambda2 may be envisioned as stretching, compressing the sheet simultaneously along the two directions of the eigenvectors with the factors given by the eigenvalues. Thereby only the directions of the eigenvectors do not change. For example, the sheet could be stretched by a factor lambda1 along the x-axis and lambda2 along the y-axis. Assuming the eigendirections being given by the directions of the coordinate axes. In two dimensions, there can be two such independent stretching directions, but they do not have to be at right angles to each other. A rotation in two dimensions is a linear map with no eigenvectors, and a shear, as in the photo, has only one eigenvector, with eigenvalue 1. Other vectors besides eigenvectors change their directions, unless the two eigenvalues are equal, in which case all vectors are eigenvectors with that eigenvalue, yielding a magnification, i.e., a linear map that alters neither shape nor direction, but only magnitude. A reflection may be viewed as stretching a line perpendicular to the axis of reflection by a factor of -1 while stretching the axis of reflection by a factor of 1. For 3D rotations, the axis of rotation is an eigenvector of eigenvalue 1. A three-coordinate vector may be seen as an arrow in three-dimensional space starting at the origin. In that case, an eigenvector is an arrow whose direction is either preserved or exactly reversed after multiplication by the corresponding eigenvalue. Determines how the length of the arrow is changed by the operation, and whether its direction is reversed or not, determined by whether the eigenvalue is negative or positive. In abstract linear algebra, these concepts are naturally extended to more general situations, where the set of real scalar factors is replaced by any field of scalars, the set of Cartesian vectors is replaced by any vector space, and multiplication of a vector by a matrix is replaced by any linear operator that maps vectors to vectors. In such cases, the vector in eigenvector may be replaced by a more specific term, such as eigenfunction, eigenmode, eigenface, or eigenstate. Thus, for example, the exponential function is an eigenfunction of the derivative operator, with eigenvalue, since its derivative is the set of all eigenvectors of a matrix, each paired with its corresponding eigenvalue, is called the eigensystem of that matrix. Any non-zero scalar multiple of an eigenvector is also an eigenvector corresponding to the same eigenvalue. An eigenspace or characteristic space of a matrix is the set of all eigenvectors of corresponding to the same eigenvalue, together with the zero vector. An eigenbasis for it is any basis for the set of all vectors that consists of linearly independent eigenvectors if. Not every matrix has an eigenbasis, but every symmetric matrix does. The prefix eigen is adopted from the German word eigen for own, unique to, peculiar to, or belonging to, in the sense of idiosyncratic, in relation to the originating matrix. Eigenvalues and eigenvectors have many applications in both pure and applied mathematics. They are used in matrix factorization, in quantum mechanics, and in many other areas. History. Eigenvalues are often introduced in the context of linear algebra or matrix theory. Historically, however, they arose in the study of quadratic forms and differential equations. In the 18th century, Euler studied the rotational motion of a rigid body and discovered the importance of the principal axes. Lagrange realized that the principal axes are the eigenvectors of the inertia matrix. In the early 19th century, Cauchy saw how their work could be used to classify the quadric surfaces, and generalize it to arbitrary dimensions. Cauchy also coined the term racine caractéristique for what is now called eigenvalue. His term survives in characteristic equation. Fourier used the work of Laplace and Lagrange to solve the heat equation by separation of variables in his famous 1822 book Théorie analytique de la chaleur. Sturm developed Fourier's ideas further and brought them to the attention of Cauchy, who combined them with his own ideas and arrived at the fact that real symmetric matrices have real eigenvalues. This was extended by Hermite in 1855 to what are now called Hermitian matrices. Around the same time, Brioschi proved that the eigenvalues of orthogonal matrices lie on the unit circle, and Clèche found the corresponding result for skew-symmetric matrices. Finally, Weierstrass clarified an important aspect in the stability theory started by Laplace by realizing that defective matrices can cause instability. In the meantime, Liouville studied eigenvalue problems similar to those of Sturm. The discipline that grew out of their work is now called Sturm-Liouville theory. Schwarz studied the first eigenvalue of Laplace's equation on general domains towards the end of the 19th century, while Poincaré studied Poisson's equation a few years later. At the start of the 20th century, Hilbert studied the eigenvalues of integral operators by viewing the operators as infinite matrices. He was the first to use the German word Eigen, which means own, to denote eigenvalues and eigenvectors in 1904, though he may have been following a related usage by Helmholtz. For some time, the standard term in English was proper value, but the more distinctive term, eigenvalue, is standard today. The first numerical algorithm for computing eigenvalues and eigenvectors appeared in 1929, when von Mises published the power method. One of the most popular methods today, the QR algorithm, was proposed independently by John G. F. Francis and Vera Kublanovskaya in 1961. Real matrices. Consider n-dimensional vectors that are formed as a list of n real numbers, such as the three-dimensional vectors. These vectors are said to be scalar multiples of each other, also parallel or collinear, if there is a scalar lambda, such that in this case lambda equals -1/20. Now consider the linear transformation of n-dimensional vectors defined by an n times n matrix A, that is, or where, for each index, if it occurs that W and V are scalar multiples. That is, if then V is an eigenvector of the linear transformation A and the scale factor lambda is the eigenvalue corresponding to that eigenvector. Two-dimensional example: consider the transformation matrix A, given by. The figure on the right shows the effect of this transformation on point coordinates in the plane. The eigenvectors V of this transformation satisfy the equation. Rearrange this equation to obtain which has a solution only when its determinant, a minus lambda I, equals 0. Set the determinant to 0 to obtain the polynomial equation, known as the characteristic polynomial of the matrix A. In this case, it has the roots lambda equals 1 and lambda equals 3. For lambda equals 1, the equation becomes which has the solution. For lambda equals 3, the equation becomes which has the solution. Thus, the vectors v and w are eigenvectors of A associated with the eigenvalues lambda equals 1 and lambda equals 3, respectively. Three-dimensional example: the eigenvectors v of the 3 times 3 matrix A satisfy the equation. This equation has solutions only if the determinant a minus lambda I equals 0, which yields the characteristic polynomial, with the roots lambda equals 1, lambda equals 2, and lambda equals 3, associated with the roots lambda equals 1, lambda equals 2, and lambda equals 3 are the respective eigenvectors. Diagonal matrices. Matrices with entries only along the main diagonal are called diagonal matrices. It is easy to see that the eigenvalues of a diagonal matrix are the diagonal elements themselves. Consider the matrix A. The characteristic polynomial of A is given by which has the roots lambda equals 1, lambda equals 2, and lambda equals 3. Associated with these roots are the eigenvectors, respectively. Triangular matrices. A matrix with elements above the main diagonal that are all zeros is described as a triangular matrix, or in this case, lower triangular. If the elements below the main diagonal are all zeros, then the matrix is upper triangular. The eigenvalues of triangular matrices are the elements of the main diagonal, in the same way as for diagonal matrices. Consider the lower triangular matrix A. The characteristic polynomial of A is given by which has the roots lambda equals 1, lambda equals 2, and lambda equals 3. Associated with these roots are the eigenvectors, respectively. Eigenvector basis. In this section, it is shown that a change of coordinates of a matrix A to O basis formed by its eigenvectors results in a diagonal matrix. Let A be an n times n linear transformation that has n linearly independent eigenvectors phi, and consider the change of coordinates of A so that it is defined relative to its eigenvector basis. Recall that the eigenvectors phi of A satisfy the eigenvalue equation. Assemble these eigenvectors into the matrix V, which is invertible because these vectors are assumed linearly independent. This means the coordinates of x and x relative to the basis phi can be computed to be. This yields the change of coordinates. To see the effect of this change of coordinates on A, introduce I equals VV minus 1 into the eigenvalue equation and multiply both sides by V minus 1 to obtain notice that which is the natural basis vector. Thus, and the matrix K is found to be a diagonal matrix with the eigenvalues lambda I as its diagonal elements. This shows that a matrix A with a linearly independent system of eigenvectors is similar to a diagonal matrix formed from its eigenvalues. Matrices. Characteristic polynomial. The eigenvalue equation for a matrix is which is equivalent to where is the identity matrix. It is a fundamental result of linear algebra that an equation has a non-zero solution if, and only if, the determinant of the matrix is 0. It follows that the eigenvalues of are precisely the real numbers that satisfy the equation. The left-hand side of this equation can be seen to be a polynomial function of the variable. The degree of this polynomial is the order of the matrix. Its coefficients depend on the entries of, except that its term of degree is always. This polynomial is called the characteristic polynomial of, and the above equation is called the characteristic equation of. For example, let B the matrix the characteristic polynomial of is which is the roots of this polynomial are 2, 1, and 11. Indeed, these are the only three eigenvalues of corresponding to the eigenvectors and real domain. Since the eigenvalues are roots of the characteristic polynomial, and matrix has at most eigenvalues. If the matrix has real entries, the coefficients of the characteristic polynomial are all real, but it may have fewer than real roots, or no real roots at all. For example, consider the cyclic permutation matrix. This matrix shifts the coordinates of the vector up by one position, and moves the first coordinate to the bottom. Its characteristic polynomial is which has one real root. Any vector with three equal non-zero coordinates is an eigenvector for this eigenvalue. For example, complex domain. The fundamental theorem of algebra implies that the characteristic polynomial of a matrix, being a polynomial of degree, has exactly complex roots. More precisely, it can be factored into the product of linear terms, where each is a complex number. The numbers are roots of the polynomial, and are precisely the eigenvalues of. Even if the entries of are all real numbers, the eigenvalues may still have non-zero imaginary parts. Also, the eigenvalues may be irrational numbers even if all the entries of are rational numbers, or all are integers. However, if the entries of are algebraic numbers, the eigenvalues are algebraic numbers too. The non-real roots of a real polynomial with real coefficients can be grouped into pairs of complex conjugate values, namely with the two members of each pair having the same real part and imaginary parts that differ only in sign. If the degree is odd, then by the intermediate value theorem at least one of the roots is real. Therefore, any real matrix with odd order has at least one real eigenvalue, whereas a real matrix with even order may have no real eigenvalues. In the example of the 3 times 3 cyclic permutation matrix above, the characteristic polynomial has 2 additional non-real roots, namely and where is the imaginary unit. Note that, and then and therefore, the vectors and eigenvectors of with eigenvalues and respectively. Algebraic multiplicity. For a definition of geometric multiplicity, referred to in this section, see below. Let be an eigenvalue of an matrix. The algebraic multiplicity of is its multiplicity as a root of the characteristic polynomial, that is, the largest integer such that divides evenly that polynomial. Like the geometric multiplicity we have, and the sum of over all distinct eigenvalues also cannot exceed, if complex eigenvalues are considered, is exactly. It can be proved that the geometric multiplicity of an eigenvalue never exceeds its algebraic multiplicity, therefore, is at most. If, then, is said to be a simple eigenvalue. If, then, is said to be a semi-simple eigenvalue. Example for the matrix. The characteristic polynomial of is, being the product of the diagonal with a lower triangular matrix. The roots of this polynomial, and hence the eigenvalues, are 2 and 3. The algebraic multiplicity of each eigenvalue is 2, in other words they are both double roots. On the other hand, the geometric multiplicity of the eigenvalue 2 is only 1, because its eigenspace is spanned by the vector, and is therefore one-dimensional. Similarly, the geometric multiplicity of the eigenvalue 3 is 1 because its eigenspace is spanned by. Hence, the total algebraic multiplicity of A, denoted, is 4, which is the most it could be for a 4x4 matrix. The geometric multiplicity is 2, which is the smallest it could be for a matrix with 2 distinct eigenvalues. Diagonalization and eigendecomposition. If the sum of the geometric multiplicities of all eigenvalues is exactly, then has a set of linearly independent eigenvectors. Let be a square matrix whose columns are those eigenvectors, in any order. Then we have, where is the diagonal matrix such that is the eigenvalue associated to column of. Since the columns are linearly independent, the matrix is invertible. Pre-multiplying both sides by we get, by definition, therefore, the matrix is diagonalizable. Conversely, if is diagonalizable, let be a non-singular square matrix such that is some diagonal matrix. Multiplying both sides on the left by we get. Therefore each column of must be an eigenvector of, whose eigenvalue is the corresponding element on the diagonal of. Since the columns of must be linearly independent, it follows that thus is equal to if and only if is diagonalizable. If is diagonalizable, the space of all coordinate vectors can be decomposed into the direct sum of the eigenspaces if. This decomposition is called the eigendecomposition of, and it is preserved under change of coordinates. A matrix that is not diagonalizable is said to be defective. For defective matrices, the notion of eigenvector can be generalized to generalize eigenvectors, and that of diagonal matrix to a Jordan form matrix. Over an algebraically closed field, any matrix has a Jordan form and therefore admits a basis to generalize eigenvectors, and a decomposition into generalized eigenspaces. Further properties. Let be an arbitrary matrix of complex numbers with eigenvalues. then the trace of, defined as the sum of its diagonal elements, is also the sum of all eigenvalues. The determinant of is the product of all eigenvalues. The eigenvalues of the th power of, i.e., the eigenvalues of for any positive integer, are. The matrix is invertible if and only if all the eigenvalues are non-zero. If is invertible, then the eigenvalues of R. Clearly, the geometric multiplicities coincide. Moreover, since the characteristic polynomial of the inverse is the reciprocal polynomial for that of the original, they share the same algebraic multiplicity. If is equal to its conjugate transpose, then every eigenvalue is real. The same is true of any symmetric real matrix. If is also positive definite, positive semi-definite, negative definite, or negative semi-definite, then every eigenvalue is positive, non-negative, negative, or non-positive respectively. Every eigenvalue of a unitary matrix has absolute value. Left and right eigenvectors. The use of matrices with a single column to represent vectors is traditional in many disciplines. For that reason, the word eigenvector almost always means a right eigenvector, namely a column vector that must be placed to the right of the matrix in the defining equation. There may be also single-row vectors that are unchanged when they occur on the left side of a product with a square matrix, that is, which satisfy the equation. Any such row vector is called a left eigenvector of. The left eigenvectors of a transpose is of the right eigenvectors of the transposed matrix. Since their defining equation is equivalent to it, follows that, if is Hermitian, its left and right eigenvectors are complex conjugates. In particular, if is a real symmetric matrix, they are the same except for transposition. Variational characterization. In the Hermitian case, eigenvalues can be given a variational characterization. The largest eigenvalue of is the maximum value of the quadratic form. A value of that realizes that maximum is an eigenvector.